Alright, to kick off the next subsection dealing with electric cells and electromotive force, go ahead and try this. Pause the video, see what you can work out here. Hopefully by now circuits are no big deal. Kirchhoff's two laws, V equals IR a whole bunch of times, and then you can get whatever it is you need to find. And our solution here, we've got 3 amps here, 2 amps here. Remember that when resistors are in series, current stays the same. When resistors are in parallel, potential difference stays the same as we would have with these two combined resistors. Combine those and then combine 3 and 4, get those, and we have potential difference of 12 across these two, potential difference of 12 across these two. So we have a voltage gain, voltage drop. Voltage can be calculated from current and resistance. Current can be calculated using total branch resistance. Current going into a junction equals the current going out of a junction. Alright, the observer effect. When taking any scientific measurement, there's always the possibility that the act of taking measurements will change what is being measured. What that means is, if you look at the tire gauge, to get the pressure on the tire, you have to remove the little cap and then plug in the pressure to get the gauge pressure on the tire. And whenever you do that, a little bit of air is going to escape, so there's no way of knowing what exactly that pressure was inside the tire. Additionally, there is something called the white coat syndrome, where the act of getting your blood pressure increases your blood pressure. Could be from nerves, anxiety, that kind of thing, that causes your blood pressure to increase as it's being read by the doctor. So as it relates to us with electricity, when we measure voltage or current in a circuit, we want to make sure to minimize the effect that our tool has on the circuit to get the most accurate results. And those tools, we have got the multimeter here, which can be split into a voltmeter or an ammeter or a galvanometer for smaller currents. There's our symbols. It's just a circle with a V for a voltmeter and a circle with an A for an ammeter. Easy, very easy to recognize. For an ammeter, the way we limit the interruption or limit the false readings, we hook it up in series with components being measured. And what this does is we're assuming an ideal ammeter to have 0 resistance. So that means the current is just going to flow through here without being impeded at all. So that way we can actually measure what is the true current. It's not a real thing, of course. You can't go out to the store and buy an ideal ammeter. There's always going to be some resistance involved. Well, what happens if an ammeter isn't ideal? Then what is the reading for the current flowing through the ammeter if it has an added resistance of 1 ohm? Go ahead and solve this circuit. So we've got 1 ohm there. The total resistance, 1 plus 5 plus 5 gives us 11, and then the total current equals 0.9 amps. This is lower than the actual current in the circuit, so the component may actually be affected. A voltmeter, to limit any kind of false reading here, what we do is we hook the voltmeter up in parallel with the component being measured. So we always say the potential difference over the resistor, or the potential difference over the cell, or over the battery. And that's because we're measuring the potential difference over this thing. So in parallel. And the idea here is that our resistance with this voltmeter is infinite. So we have infinite resistance in an ideal voltmeter, and what that does is, if we follow the current, when given the choice to go towards the infinite resistance where it's never going to get through, or go through the resistor, it's just going to travel through the resistor. It's not going to go to the infinite resistor. Alright, what if the voltmeter isn't ideal? What's the reading here across R1 if the voltmeter has an added resistance of 20 ohms? Let you go ahead and try that. Here we go. potential difference is the same in parallel. So that means 20 ohm, or whatever our potential difference down here is, potential difference up here is. So there we go, 4.5 volts. This is not a true reading of the total resistance here. Because we've added this in as an extra resistor, we then have to combine it with R1, which is in parallel, so we're inversing plus the inverse, and then taking the inverse of that, and we get 9 ohms. Alright, here's another one for you. Ah, it cheated. Let me go back and fix it.